Okay, today we're going to talk about a different kind of product of two vectors, and this is called a cross product. Okay, and the symbol for a cross product is the times symbol that you learned like in first grade, that looks like an X. Okay, let me show you how to calculate this. So suppose we have two vectors. Now we're only going to do this with three-dimensional vectors. Okay, we're not going to do it with two-dimensional vectors. So let's say we have u is, let's say, this vector, u1, u2, u3, okay? And let's say v is the vector with components v1, v2, v3. Okay, so we say u cross v, and here's what it equals. So first of all, it equals a vector. That's the first thing to know. Remember, the dot product of two vectors is a scalar, and so sometimes that's called scalar product. But the cross product of two vectors is a vector, and so sometimes this is called a vector product. Okay? Now, what goes in these three numbers? That's what I need to show you. Okay, I'm going to stretch this out a lot so we have more space. Okay, the first component, you're just going to need to learn this formula. Okay, the first component is u2 times v3 minus u3 times v2. And then the second component is u3 times v1 minus u1 times v3. Sorry about that. And the third component is u1 times v2 minus u2 times v1. Okay? So however you can remember that formula is fine. The book goes into one way of remembering it using something called determinants. But we don't need determinants for this. All we need is that formula right there. And so I don't want to get into determinants right now. That's something you learn in linear algebra. And I suspect we might need it later in this class, but I would prefer to wait until then. So I'm not going to talk about determinants. You see it in the book if you want, and that's fine to go ahead and read it, but I'm not going to put it in the lecture. Okay, I'm just going to say to you that this is the formula for cross product. Okay, and so whenever you calculate a cross product, you follow that formula. Okay, so let's practice. Suppose we have two negative 1, 4 cross 3, 2, 5. Okay, so let's see what that would equal. So we do negative 1 times 5 minus 4 times 2. Okay, let's just write that down here. Negative 1 times 5 minus 4 times 2. So that's negative 5 minus 8, so that's negative 13. Okay, let's find the middle component. All right, for the middle one, we have 4. Oh, it looks like I left a number off up there. Let me fix that. That v should have a v1. There we go. Okay, so we do 4 times 3 minus 2 times 5. 4 times 3 minus 2 times 5. So that would be 12 minus 10, which is 2. So that goes in the middle. Okay, and then the third component. Okay, so for that we have 2 times 2 minus negative 1 times 3. 2 times 2 minus negative 1 times 3. So that'll be 4 plus 3, which is 7. Okay, and that's how you do cross product. Now here's something interesting. Let's do the cross product of the same two vectors, but in the other order. Let's do 3, 2, 5 cross 2, negative 1, 4. Let's see what we get. Okay, so the first component will be 2 times 4 minus 5 times negative 1. 2 times 4 minus 5 times negative 1. So that's going to be 8 plus 5. So what is that? That's 13, right? Oh, look at that. You can probably guess what's going to be happening here. All right, let's do the next one. The next component will be 5 times 2 minus 3 times negative 1. 5 times 2. Sorry, I didn't mean to move that around. Let me see if I wrote that one right. Let's see, 5 times 2, that's right, minus 3 times negative 1. Oh, I see what I did wrong. I'm sorry. It's not 3 times negative 1. It should have been 3 times 4. Sorry about that. That looks much better what I knew it was supposed to come out to be. That's going to be 10 minus 12, which is negative 2. Okay, now you can probably really guess what the third component is going to be. But let's calculate it and see if you're right. So for the third component, we have 3 times negative 1 minus 2 times 2. 3 times negative 1 minus 2 times 2. So that's negative 3 minus 4. We get negative 7. So do you see what happens when you change the order of the vectors in a cross product? You end up changing the signs in the answer, which means, by the way, what is the relationship spatially between these two vectors? They're the same length and they point opposite directions of each other. Okay? So that's one thing to remember. This is a good thing to remember, that V cross U is the opposite of U cross V. Okay? Let me actually, so by the way, so that's an algebraic property of cross product. Okay, and that property is called anti-commutativity. Remember how if you can swap the order, it's called the commutative property. If swapping the order changes the sign, that's called the anti-commutative property. And what I'm going to do is I'm going to show you now 7 algebraic properties of the cross product. Okay, here's Theorem 89 from the book. And you recognize number 1, that's the one I just showed you. When you change the order in a cross multiplication problem, you get what you could say the same vector but with opposite signs. And so what that means is you get the opposite vector. Okay, same length, pointing in the opposite direction. Okay, let's look at the next one. If you do a cross product of a sum of two vectors, which is what, by the way? Let me erase that. When you do vector u plus vector v, what do you get? You get a vector, right? And they're saying, what if you did the cross product of that vector with a third vector? Okay? It's the same answer as if you added the cross product of u with v plus w, plus the cross product of v with w. So what we're saying is you could calculate something like that, or you could calculate like that. Whichever is easier, you're going to get the same answer. Okay, and likewise, likewise, if you want to do the cross product of a vector u with a vector that is two vectors added together, okay, you could also add the cross product of u with each of the individual vectors. You'll get the same answer. Okay? All right, if you take a cross product, that's a vector, right? You want to multiply that vector times a scalar? That's perfectly fine. You may choose, if you prefer, you can choose to just take the first vector and multiply times your scalar, and then do the cross product of that with v. Or multiply v times the scalar, and then do the cross product of u with that. All three of those will give you the same answer, so you can do it whichever of the three ways that you want. Okay? All right. Let's look at number 4. This is a combination of a cross product with a dot product, which means the answer will be a what? A scalar. Because look, u cross v, that's a vector. Cross products always give you vectors. And then that's a dot product with a vector u. Dot products always give us scalars. So the answer is going to be a number. Now notice what they're saying here. We're dotting with one of the vectors that was in the cross. And when you do that, you're automatically guaranteed to get the answer 0. You can try it out yourself and see, but I guarantee you it's going to come out to 0. Okay, and this is telling us the same thing, except they're dotting with v, which is one of the vectors in the cross. Okay, if you do a cross product of two vectors and then take that answer and do the dot product with either one of those two vectors, you're going to get 0 every time. Okay, number 5, what if you do a cross product of a vector with itself? You're going to get 0 again, but look at that. That's not the number 0, right? It's the vector 0, because a cross product of two vectors is always a vector. So if you do a cross product of a vector with itself, you're going to get 0. I'll take it even a step further. The cross product of any vector with a vector parallel to it will be 0. Let me add that here. That's right. If u is parallel to v, then u cross v will be the 0 vector. And since u is parallel to itself, then u cross u gives you the 0 vector. All right, what else gives you the 0 vector guaranteed is if you cross anything with the 0 vector, you'll get the 0 vector. Okay, and finally, This is called a triple scalar product. You have a vector u dot with a vector which is a cross product of v and w. That's called a scalar triple product. It's easy to see why it's called a triple product. Why is it called a scalar triple product? Because that's a vector and this is a vector, and when you do the dot product of two vectors you get a scalar. Okay, and what this formula is telling us is that it actually doesn't matter where you put the dot and the cross. You'll get the same answer either way. It does matter, though, I should point this out. It does matter which one you do first. You have to do the cross product first. Let me write down something that would make no sense. There's no such thing as that, which I just wrote down. And the reason why is because u dot v is a what? A scalar. You can't cross product a scalar with a vector. Okay? All right. Now, the next thing I want to talk about is, let's just scroll back up for a minute here. What is the relationship between this vector that you get from the cross product and these two vectors that were in the cross product? What's the relationship between them? Okay. It's a very interesting relationship. Oh, that should be one word. Okay, let's draw a couple of vectors here. Let's draw vector u as a, how about a green vector? Now remember, this is in three-dimensional space, not two. Maybe even I should put, let's pause for a minute here and let me put some axes here. Okay, now let's draw a vector and let's call that u. And let's draw a vector for v. Let's make that one magenta. Okay, now, what's the relationship between those two vectors and the vector u cross v? Okay, there's, I can say 3 or 4 very important things here. Number one, u cross v is orthogonal to both u and v. Okay? It's orthogonal to both of them. Remember, orthogonal means perpendicular. So vector u cross v has two possibilities. it might be sticking up in such a way like this, so that you have a right angle here between V and U cross V, and also a right angle, it's hard to draw them both, a right angle between U and U cross V. Now, to your eyes, that doesn't look like a right angle, but that's because it's drawn on 2 dimensions. Okay, but imagine that in 3-dimensional space. Let me see if I can maybe draw those 2 squares to indicate the right angles a little bit better. So there would be one here. Okay, and then another one like that. That's a little bit better. Okay, so that's one possibility of how of what direction U cross V could be pointing. There's another possibility. Can you guess what? There's one more possibility, what it is? It could be pointing exactly the opposite direction. Okay, now which one is it? So I'm going to give you a rule called the right hand rule. I'm going to put in parentheses here, R, H, R, for right hand rule. If I was with you in a classroom, I could show you a demonstration that would make this perfectly easy to understand, but over the computer it's not. So I'm going to explain it with words very carefully. Please listen carefully. I'll go ahead and give you some advice too. If you don't understand what I'm about to say, then just go to YouTube and just type in right hand rule. There's probably a video of somebody showing it to you as a demonstration. Okay, but here's what you do. Okay, for U cross V, okay, imagine placing your right hand so your fingers point in the direction of U, and your palm faces V. Okay, so can you imagine that? Please imagine it right now. Please imagine placing your fingers right along vector U. So the heel of your hand, your wrist, will be right at the origin, and it'll look like the green vector is shooting right out of your middle finger. Okay, but you could rotate your hand so that the palm is facing any direction you want, right? So now imagine rotating your hand so that your palm is facing vector V. Okay? Now with your hand right in that position, make a thumbs up symbol. Okay? Okay? Now, your thumb indicates the direction of U cross V. That's the right-hand rule. So in our picture there's a dark blue and a light blue vector. Which one of those is u cross v? Just think about doing it right now with your hand, what I described. And which way is your thumb pointing? So this one up here would be u cross v. Okay? That other one, the light blue one, what vector do you think that one is? That would be the vector v cross u. Okay? That's the right-hand rule. So once again, if you need to see that with your eyes, then just look up a video of right-hand rule on YouTube. You'll find one, I'm sure. Okay? I'm going to erase v cross u and leave u cross v. All right, now, so that's important. That's a very handy relationship of the direction of u cross v compared to the directions of u and of v, okay? All right, there's more of a relationship. Sorry, it's taking a long time to erase this stuff here. I don't know why. Here, let me pause the recording so I don't waste your time. Okay, so something else to say about the relationship here. Okay, so let's call this number 1. Okay, so number 2. So number 1 tells us which direction u cross v is going to point. What can I tell you about the length of u cross v? All right, let me tell you two things about that. So first of all, wow, I don't know why my pen is just really not cooperating very well. Shoot, okay, I'm going to pause again and let me figure this out. Okay, I think it's going to work better now. Okay, so the magnitude of u cross v, well, it's not working better. Okay, I think it's going to work better now. I put in a new battery. And don't worry, I deleted the axes on purpose. Okay, so the magnitude of u cross v is equal to, now this will look maybe a little bit familiar to you. Don't let it confuse you. It equals the magnitude of u times the magnitude of v times the sine of the angle between u and v. Doesn't that look familiar? Because we had an almost identical thing with the dot product, which was the absolute value of the dot product of u and v equals the magnitude of u times the magnitude of v times the cosine of the angle between them. So see, very, very similar rules. So what's that tell you? It tells you you can use the dot product or the cross product to find the angle between u and v. Either one will work. It's just that one involves cosine and the other involves sine. But dot products are a lot faster to compute than cross products. So if that's what you're wanting to find is angle theta, you're really better off using this formula, in my opinion. But that formula there that's labeled as number 2 is actually still very helpful because, let me show you something that's a little surprising. That also equals the area of really slow because my pen is just not working well, even though I just changed the battery. Okay, the area of the, now because the pen's not writing well and this word is long, I'm going to draw a picture instead. This is a parallelogram. Okay, spanned by U and V. So what do I mean by the parallelogram spanned by U and V? So what I mean is this parallelogram right here. Okay, that's called the parallelogram spanned by U and V. And the magnitude of this vector equals the area of that parallelogram. That seems surprising, but let me show you why that's true. It is surprising until you think about it, and then it actually is going to make sense. It all comes from this formula right here, okay? Because, look, let me draw a parallelogram. I'll just draw this one flat, okay? Let's just look at this. Now, if you remember from high school, let's draw a dashed line down here. Okay, the area of a parallelogram is simply this length times this length. Base times height. Let me do a better job of that one. Okay. Okay, so that's how you find the area of a parallelogram. Well, if you do this here, I'm disappointed that I put the green color on the height because I wish I would have put it on the base. So let me change that. Well, here's the point that I was wanting to make was this. Let's put vector u right along the bottom. Wow, this is really starting to turn frustrating. Okay, let's put vector u right there. Okay, then how long is the base? That base is whatever the magnitude of vector u is. That's how long the base is. Okay, let's put vector v right here. Oh, for heaven's sakes. Hold on a second. Okay, there we go. We'll put vector v right there. Okay, so the question is, how long is the height of the parallelogram? Well, let's put here theta. Let's put theta right here. Okay, if this is vector v there along that left-hand side of the parallelogram, that's vector v. Now, before I say anything else, let me make sure I don't confuse you. Along the bottom, I put magnitude of u, but on the side, I put vector v, no magnitude, right? I should maybe clear that up. So the object, which is the arrow along the bottom, is vector u. The length of that is the magnitude of vector u. Okay? All right, now, on the side, we have vector v, is the object, the arrow. Okay? The length of that arrow is the magnitude of vector v. What is the height then? Well, simple trigonometry tells us that that height is the magnitude of vector v times the sine of theta. So when we say the area of the parallelogram is base times height, that means the area of the parallelogram is magnitude of u times magnitude of v times sine of theta. Okay? So that's where that surprising result comes from. So now you have a very simple way of finding areas of parallelograms, provided that you can come up with two vectors that emanate from one of the corners and lie along sides of the parallelogram. Okay? And by the way, you can even use that to find areas of triangles now too, because look, what if you wanted to find the area of this triangle right here? Well, that triangle is just half of the parallelogram spanned by u and v. So the area of that triangle is half of the magnitude of u cross v. Okay? Very nice that you can use this stuff to do geometry problems. Okay, now one more thing that I'm going to tell you. I'm going to erase the vector u cross v. Let's put on here a new vector, a third one, which we'll call w. I'm just going to put it like this. Now I'm going to attempt to draw a picture that I find very difficult to draw. So I'm going to pause the video so you don't have to watch me try to draw it, because it might take me several attempts. Okay, you see that shape there? That is called a parallelepiped, spelled like this. Parallelepiped. Spanned by u, v, and w. Three vectors. Okay. Now I'm going to tell you something. It wouldn't make any sense to talk about the area of that, right? Because that's three-dimensional. It would make sense to talk about the volume. All right. How can you find the volume of that? Well, the volume of that parallelepiped is equal to the absolute value of the scalar triple product of u, v, and w. So I'll write it like this: u dot v cross w. Okay? So that equals the volume of the parallelepiped spanned by U, V, and W. So you're going to get questions on Newton that ask you how to find different things like areas of parallelograms or areas of triangles or volumes of parallelepipeds, okay? And this is how you find them. Okay, I think we're going to stop there. There's one more thing I want to cover, which is torque, but that's a physics concept, and I like how in the previous section we did work as a separate lecture, so we're going to do torque as a separate lecture as well. Also, this lecture is already 40 minutes long anyway, so let's stop here, and then I'll post this, and then the next lecture will be about torque, which will be a relatively short lecture, I suspect.